Thank you very much for this invitation. I'm very happy to be able to talk at this PRAIRIE Colloquium, even if it is at distance. I will talk about machine learning seen from the point of view of statistical physics, which I have been working on for several decades. And exceptionally, I will do something that I should not be doing probably, but considering the exceptional circumstances, I will also add an appendix to this main talk, and the appendix will be about inference methods in order to improve COVID-19 tracing. It is connected to the machine learning talk, but it is slightly different. So, machine learning, I will be talking about standard supervised machine learning, in which we have a machine. The machine is presented with an input, it delivers some output. The machine itself depends on many parameters. So, for instance, as we all know, one standard example of such machine learning would be to present pictures and have a machine that is able to identify what there is in the picture. You present a picture of a cat and the machine answers cat, and you present the picture of a dog and the machine answers dog. A big breakthrough has been made on this identification and analysis of images in the last decade or less, and this was based on the use of special kind of machines which are deep neural networks. Deep networks, they are organized, they are artificial neural networks in which we have some simple units like artificial neurons, like the one presented here on the right. These units, this neuron will receive the input here from three other neurons. X1, X2, X3 are the activities of each of the input neurons. And depending on this activity, the output of our neuron will be done in two steps. It will first compute a linear combination, J0 plus J1x1 plus J2x2 plus J3x3. So this linear combination depends on the activity of the previous neurons and on four parameters: the weights J1, J2, J3, which are the weight of the equivalent of the synaptic efficacy, and a bias J0. So there are four parameters for this neuron. And then one applies a nonlinear function. It could be a sigmoid function. A very popular one is the one described here, which would be the rectifying linear unit. So you should imagine that you have a network like that with the neurons organized in layers. There are hundreds of layers, there are hundreds of thousands or millions of neurons. You have then to fix, to find the correct values of all the parameters. So the parameters are associated with each edge on this graph, because this edge characterizes the strength of the transmission of information from this neuron to that neuron. So this parameter has to be fixed. So I have a machine which contains millions of parameters. And in order to fix these parameters, this machine is trained on a very huge database. And basically it is trained by minimizing the training function, which is the number of errors that are made on the database. For instance, I have a large database of cats and dogs. I compute for a given value of the J parameters, of all my parameters, I compute the performance of the machine, how many cats and dogs are correctly identified, and I try to optimize this performance. Usually this is done by simple gradient descent type algorithms. Do we understand how this works? Well, you can look at one of these very successful deep networks, one that is used for analyzing images, for instance, and you will realize that it is very well organized. You can look at the various layers of neuron. You understand. You can measure. You can have memorized after training. You know all the synaptic weights, all the parameters of the machine. So you know all these 1 million parameters, and you know very precisely everything of this machine. If you present some input, you are able to compute easily what will be the output of the machine. In some sense, if you think about it in terms of neuroscience, this would be the absolute dream of the neuroscientist. It could be a case in which neuroscience is able to look at every single neuron and the efficacy of the synaptic transmission from this neuron to all other neurons. This is spectacular, but as I will argue, I think that in spite of knowing everything, we understand very little of how it works. And basically, for instance, in terms of designing the network, deciding what is the architecture of the layers, or what are, if a neuron, what are the other neurons to which a given neuron is connected, what are the weights, what are the various symmetries involved. All of this we know very little. We have some kind of accumulated practical knowledge, but basically we have not made much progress about this in the last few years.
Okay, so we have this input psi. It goes through a machine. This machine depends on a lot of parameters. W could be 1 million parameter, and it gives some output. The output could be just a label, cat or dog, or a bit more complicated label than that in other practical tasks. And the training goes through presenting the database, and the database is built from a certain number of examples of pairs, input, output. So I label them by the index mu. I have pairs of input, which could be images. For the image psi mu, I know what is the output. I know the label. That is, I have someone who has carefully looked at all the images of the database and told me if there is a cat or not in the database. So this is called supervised training. That is, on the database, we know what should be the output. And basically, we can train the machine by several processes. We will want to find the set of weights, the set of parameters of the machine, such that the performance of the machine is optimal on the database. So for instance, I look at all the images of the database. I look at what is the output produced by the machine. This is this function f, which depends on the weight and on the input. And I compare it to the desired output, y mu. And I can take what is called a loss function, a penalty function. Physicists call it an energy function. It could be here just the square of the difference, but you could have better loss function adapted to other problems. This is also part of the practical knowledge. A slightly different approach, but very deeply related, would be to look at it from the point of view of inference. That is, you have some prior on the space of the weights, W, for instance. You will put a weight, you will impose that the weights cannot become too large. From this prior, then you add some accumulated evidence, which comes from each image of the database, and you will put a experimental weight due to the evidence, and it could be written here as exponential minus beta times the energy. You see that I take the notation of the physicist, but basically beta is a parameter which in physics is the inverse of temperature. That you can look at it as a parameter. Of course, you look in the large beta limit, you will put the whole weight on the set of weights of parameters of the machine, such that the machine does perfectly on the database. And then you can look at the posterior probability of the weights, W, given the database, and it takes the form that is written here on the slide. People sometimes criticize the Bayesian approach, saying, well, there is the story of the prior and so on. I think it is perfectly valid. In all the approaches, there are a lot of priors. And I want to mention and underline that there is, in all what we are doing in deep learning at the moment, there are enormous priors. And the big one is certainly the architecture. That is the person who decides, let me try with 150 layers, and the first one will be a convolution net, and the second one, etc., etc. And I will then train all these machines. All this is an enormous prior, which is accumulated knowledge from the last decades. And it is a very important practical knowledge, but it is not based on science because there is no real theory on that. I remember listening to Yann Lequin's lecture at Collège de France, where he was saying that it's a bit like when there were steam engine before the invention of thermodynamics. A steam engine existed for 150 years before invention of the theory of thermodynamics, and they were certainly of practical use. So we are probably at this stage. I don't know if it will take another 150 years. I hope that a little bit of progress will be made in the next decade, let's say, so that I can see it. The second stage, of course, which is a crucial one, is not only to be able to perform well on the database, on the training set, but also to generalize correctly. And generalization is tested typically by taking a new set of examples, new data on which the machine has not been trained, again with labels, and seeing if the error on this new set of data is small or not. There are two main issues that have to be addressed. The first issue is algorithmic, that is how to find the minimum of the training loss function, or how to generate W's which are typical for the probability distribution that I have written here. And the second one will be more theoretical. What is the performance? What will be the generalization error? Can we bound? Can we understand how the performance scales with the size of the network, the size of the database, maybe the nature of the database? All these are absolutely crucial questions. Let me emphasize that from the point of view of statistical physics, the problem of learning that I have described in this first slide is typical of a problem of statistical physics. It's actually a problem of statistical physics of disordered systems. That is, I have a large set of W, a large set of weight, 1 million variables. They could have a prior, let's say, Gaussian distribution, whatever. And then they interact with this energy function. And this energy function, you see that it depends. There is one piece of this energy function for each image in the database, the image and target label. And so this energy function, it depends on a lot of parameters, which is the full database and the desired target labels. So this is what in physics we call a disordered system. It's a system in which we have many variables. Optimizing, finding the most probable W in a 1 million dimensional space like that is in general very hard, except when we have placed ourselves in the case where it is just the energy is just convex. That would be the simple case. Unfortunately, it's rarely the case, and it's not the case for the deep networks. In general, it's a very hard problem. And it's even harder because of the fact that this energy function depends on all these many parameters that we call in physics quench parameter, which are the images and their label. They are quenched because they do not participate to the probability distribution. They are just auxiliary parameters. They are frozen once for all. And what one wants is, for a given database, find the best W. So this is a given database is a sample of a problem, and with a new database, I have a new problem, of course. So this is to motivate the next 4 slides, which will be slides where I will very briefly present some ideas of statistical physics and why, just to help understand why statistical physics can be helpful to some extent for these problems. Let me start by simple ideas of statistical physics. Maybe it's interesting also to underline what is the significance of a model in statistical physics. For instance, what would be a model of a magnet? Well, this has been worked out 100 years ago. A magnet is a system in which you have elementary magnetic moment, atomic molecular magnetic moment, that in simpler case can be just point up or down, say, and they will interact. And so in the model of a magnet, a simple model of the magnet would be just to represent the magnetic moment by a binary variable, SI, which is +1 if it points up and -1 if it points down. and then assume that there is a simple interaction energy between neighboring spins, because we call them spins, and this energy is such that the energy is lower when the spin points in the same direction. This is called an exchange energy. And so basically you can look at the probability of a spin configuration. You take spins on a lattice like that, and this probability is described by exponential minus the energy over the temperature. So as you minimize the energy when two spins are aligned, of course, the ground state, the configuration of lowest energy, is when all the spins point in the same direction. There are two ground states. Either they all point up or they all point down. But of course, these are just two configurations. But if you relax a little bit, if you look at configuration in which 10% of the spins point in the wrong direction, that is, you have 90% up and 10% down, there are many such configurations. And so there is an entropy associated with that. And the whole game of statistical physics is to understand, in some sense, the interplay between energy minimization and the entropy maximization. And this is what triggers the behavior of the model. And so what happens in a ferromagnet is that at low temperature, the spins align, and you see all these microscopic magnetic moments, they come together. And so you find a macroscopic magnetic moment. So you find you can use it to orient yourself in the magnetic field of the Earth, for instance. And you can, now I can try to ask what would be a simple theory of that. This was found 113 years ago by Weiss. A theory would be just assume that you have a system which is homogeneous, and assume that the expectation value of the spin is m. And if you look at a spin in the presence of its neighbors, it's easy to see that the expectation value of that the magnetization is the expectation value of the tangent of the contribution of its neighbors. And there is an approximation which is called mean field, which is just approximating the expectation value of the tangent by the tangent of the mean itself. This gives me a self-consistent equation for the magnetization. It is a famous Weiss equation, Curie-Weiss equation, m equal tangent of z, which is the number of neighbors of a spin, j, which is a coupling constant, and the magnetization. If you solve that, you find that there is a critical value of the temperature. Oh, sorry, there should be Cj over T here. If the temperature is small enough, you have two solutions and you have a magnetized state. If the temperature is larger than the critical temperature, you have zero magnetization. This is observed in nature. This is how the magnets work. If you take a magnet and you heat it up too much, it will demagnetize. That is very well known. In the end of the 70s, people started to try to understand more complicated systems in which you have spins which interact, but they are disordered systems. So you have the magnetic moments are impurities, like impurities of manganese in copper, and the interaction between the spins of the manganese, it turns out that they depend on the distance between these two spins. And for some values of the distance, the spin want to be, the energy is minimized when the spins are parallel, but at other distances, they need to be anti-parallel. So we have conflicting constraints. And so this is more complicated. This is called a system called spin glasses. It's the same description as before, but the main difference is that you have coupling constants here, which have do not any longer have just one single value, the exchange coupling, but take many values. There is a one value for each pair. One example which has been worked out very deeply is the so-called Sherrington-Kirkpatrick model, the SK model, where the coupling constants are drawn from a normal distribution. This is important because it gives us a probability ensemble. That is, if I want to generate a sample of the Sherrington-Kirkpatrick model, you have to generate all these couplings, IID, from this normal distribution. And this gives me a sample, and then I want to study the thermodynamics. And one thing which is very important is that almost all samples, they have the same thermodynamics. They will have the same typical energy, typical entropy or what is summarized in what is called the free energy. The free energy is given by this expression. And basically, if you ask, if you take many samples and you ask what is the probability to find a sample with a certain value of the free energy density, it is given by, it is governed by a large deviation principle. It means that there exists a large deviation function phi of f, such that the probability of finding a sample with a given free energy is given by e to the n phi of f. And so when n is large, the probability is completely dominated by the maximum of this function phi of f. And it means that almost all samples that you will observe will have this f star free energy. And almost all samples also have the same thermodynamic properties. If you build a sample of copper manganese and build another one, you dilute manganese in copper, you do two samples, you will find that they have the same magnetic properties, they have the same thermodynamic properties, the same specific heat, and so on. There is one method that has been used a lot and that is absolutely essential in all these. There are two methods that are essential. The first one is the one I described here. It's called the replica method. In the replica method, basically one way of looking at it is to say, I want to reconstruct this large deviation function phi of f. And in order to do that, I can look at the nth moment of the partition function. And using Laplace method, this will give me the Laplace transform of the phi of f. And basically, in the limit when n goes to 0, this will be dominated by f star. It will give me the typical free energy density. And this is a method that has been turned into an extremely sophisticated tool, and I will use it later on for application. So using that, for instance, for the Sherrington-Kirkpatrick model, you find that depending on the bias in the coupling that was in the coupling distribution and the temperature, you have several phases of the system. You have the paramagnetic phase where there is no magnetization. You have the ferromagnetic phase, like in usual magnets, where the spin align in one given direction. And then you have this strange spin glass phase, or spin glass plus ferromagnetic phase. And this is a phase in which the situation is much more complicated. There are many minima of the free energy. One way to address this phase is also to use a mean field equation developed in the context of the cavity method. And this mean field cavity method, they go as follows. Of course, you cannot write an equation for just the local magnetization because it is inhomogeneous. Every spin has its own magnetization. So you have to write a couple sets of equations. It turns out that the correct way of doing it is to look at the local field on the spin I in the absence of J, and recursively compute how it is related to the local field on its neighbors in the absence of I. This gives these coupled equations, and these equations are called the cavity equations or the belief propagation equation, and they can be turned into efficient message passing algorithm. So as a cartoon, basically you can remember that if you have a simple homogeneous system, the energy as function of magnetization has two minima. This is a Ising model. At low temperature, it will be a magnetized phase with spins pointing in majority up, and the symmetric one. But in the spin glass, you have many possibilities of many minima organized in a hierarchical structure and many metastable states. This simple case here is due to a symmetry in the problem that enforces the symmetric curve. And this one is the one that appears typically when you have strongly disordered systems. So let me go back after this parenthesis. Let me go back to the learning in the deep networks. So I have the set of weights of the network. These are my variables. They are described by this probability distribution. The disorder is huge. It's due to all the details of the database. And first approximation, if you ask someone trained in statistical physics, what will happen in this problem, the person will tell you, well, the energy should be very complicated. It's an energy in a 1 million dimensional space. It's complicated to draw and particularly to project in 2 dimensions. Nevertheless, it should have this very weird behavior with many potential minima, with many metastable states and so on. And in particular, what we know from spin glasses is that in general, finding the ground state, finding the optimum, finding the one that minimizes this energy, which is our training error, is extremely difficult. It is an NP-hard problem, but in practice, it is also very complicated. So this question of what we call the energy landscape is the first question that comes to the mind. The thing that is very strange in the deep network, that it has been found that, in particular, if you go to networks which are deep enough, which have a large enough number of layers, then they can be trained by simple methods like stochastic gradient descent, by some version of gradient descent. That is, you go in this landscape and you do some gradient descent, and you find some set of weights which have zero energy, which have zero error in the training set. So it means that the landscape is not the one that I have shown here, and there are many people working on this landscape for practical database and so on. And but I would say that at the moment there is no clear vision on how this landscape depends on the problem, on the architecture, on the database, etc. There are conjectures. Certainly, there are many minima which seem to have equivalent performance. There are some indication that there may be some flat regions around these minima. There are certainly indications that you don't have metastable states. At least there are directions in which there are no metastable states. But this is one of the first. This is the first puzzle that I wanted to mention. The second puzzle is about generalization. If you look at the number of parameters, you have so many weights, so many parameters that you can tune in your deep network that from the point of view of statistics, you work in an over-parameterized regime. That is, you have more parameters than constraints. So from this point of view, this is one of the reasons why learning is not that complicated and you don't have this very big spin glass nightmare. But on the other hand, when you do that, typically it should lead to a very bad generalization. That is what you do when you do that. You have many parameters, you are doing overfitting. And in principle, what we know in statistics, what we learn in statistics is that if you look at, here is the training error, that is what you do during the training phase, as a function of the number of parameters, the number of weights, the size of your fitting function, if you want, then you can, when you increase the number of parameters, of course, the training error diminishes and can go to zero. But in principle, what you are also told is that initially the generalization error also decreases, but at some point, what you have done is that you have done overfitting. That is, you have tuned your parameters to the database, but you present new images and it does not recognize it. So this degrades generalization. That is the standard picture. There is this apocryph quote by von Neumann that with 4 parameters I can fit an elephant. Here I am using 1 million parameters, so I don't know, I can fit certainly anything. Still, in practice, what is found in some of the networks, feed-forward networks, at least in the simple case where you have 2 layers, where it has been studied a lot, you find something which is quite different. You find that the generalization error decreases. It may have some kind of local maximum, but then when it crosses the point when you have more or less as many parameters as data, it goes down again. And so you have this, what is called double descent phenomenon. I will come back to it later. So machine learning theory has brought quite a lot of important statements, some general statements about, for instance, the fact that a 2-layer network is not good enough, is strongly limited to linearly separable problems, some complexity results, some bounds. But I want to ask, what is it that statistical physics can bring to the field? And I think it can bring several things. First of all, a lot of experience in optimization in large dimensional space. So all these ideas of landscape, also the ideas of learning dynamics, stochastic gradient dynamics is typically something that has been studied a lot in physics. And also, in some case, some precise statements for the asymptotic regime, or what I call the thermodynamic limit. Are there phase transitions, like we saw in magnet? What is the behavior of the learning dynamics? The second part, it requires something important, which is an ensemble to model the data. And I want to stress this question of ensemble. That is, I go back to learning, to generating W, which are sampled from this probability distribution. If I look at algorithmic studies, my colleagues who do that, they will typically work with a database, maybe several databases. And they will say, okay, you have this algorithm, it performs well on NIST, it performs well on SciFar, it performs well on the ImageNet. So very much adapted or very much experienced on one given database. If you want to do theoretical analysis, it's very difficult to do theoretical analysis on the distribution, which is the distribution of the cats, because we don't know what it is. So what we know, what we need is a probabilistic model of the world, of the data, of the input. And in general, this is represented by a set of independent patterns, which are drawn from some probability. You generate the image, and then you generate the label given the image. This is what is called the ensemble in physics. It's a generator of quench disorder. In all the studies that were done especially by physicists working on neural network in the 80s and 90s, all these input patterns, the database, they were generated with IID entries, typically normal IID entries. And I think this is certainly one of the limitations. Still, nice work can be done with that. For instance, I will just very rapidly remind one thing about the perceptron. So the perceptron is just a single layer of weights. There is just the input connected to the output. You take the product, the dot product of the vector W times the input vector, W dot psi, apply the nonlinearity, and this gives a Y. And in a lot of works, there was this question of the teacher-student perceptron. The teacher-student perceptron is such that you have the W star. This is the teacher. The teacher has a certain set of weights. For a given input generated randomly, it computes the label Y with the weight W star. Sorry, there should be a star here. And then the student, it has the same architecture with a weight W. And if you present the same input as a teacher, it will compute the output as f of W psi. And the whole question is whether if W, the set of weights of the student, is the same as the teacher, then the student will do perfectly. And basically the performance teacher versus student will depend on the angle between W and W star. This has been analyzed quite in detail. There has been this replica analysis. Basically, you do statistical mechanics in the space of the weight, of the student's weight, and you can analyze the properties of the Gibbs measure. This gives some result. Typically, I will show one kind of result. The result that you can obtain are obtained in the thermodynamic limit. So this is the limit in which the number of weights goes to infinity, the size of the database called P goes to infinity at a fixed ratio alpha equal P over N. I really apologize that here I am using the standard physicist notation. The number of parameters of weights of the network is N, and the size of the database is P. And generally in statistics, it's the other way around. The size of the database is small n, and the number of parameters is often small p. So imagine that large N is small p and large P is small n. I'm sorry about that, but that is an accumulation of decades of work. You can compute the phase diagram, and you can devise also a learning algorithm using the cavity equations. This is typical of the result that had been obtained. This is from 1990 from Georgia. The generalization of this teacher-student perceptron. So you look at the student perceptron, you have trained it on the database, and you find that its generalization error, it decreases. The alpha is the size of the database. When alpha increases, the error decreases, so it performs better. And at some point, the theory, the The phase diagram tells you that when you reach this threshold here, which is 1.245, the error should go to 0. These are the case of binary perceptron. The weights are taken from plus or minus 1. And then the error is 0. It has learned perfectly the task that it was supposed to do. The white points are the ones from the algorithm, iterating the message passing equation. They do perfectly when you are still in the phase where it is not supposed to transit to the perfect solution. And then they overshoot, and you need a bit more examples before it has its own phase transition. This is a phenomenon that is very well known in physics. There is an equilibrium phase transition here, and there is what is called a dynamical phase transition, which is a bit above. Here they go up to 1.49. So these are interesting results. They have been conjectured 30 years ago by using replica and cavity method. The proof has come only recently, but it has been confirmed. If you look at the same problem with continuous weight, you will find interesting prediction, like what is the generalization error as function of alpha. It does not go to 0 because it's no longer a binary weight, it's no longer a discrete space, but it approaches 0 like 1 over the size of the database, which is much better than the typical bounds that are known, which go like 1 over square root of the size of the database. So all these, you give an example, these are nice results. They are not extremely useful for understanding realistic networks. And in some sense, there has been quite some decoupling between theoretical results and practical engineering applications, starting from the 90s. So I go back to the question, the big question that I want to try to answer one day, which is why does it work? Why does deep learning work? And I think that there are 3 ingredients that have to be addressed. One ingredient is the architecture. The second one is the type of algorithm that you use for training. And the third one is data structure. And I want to focus on the third one because I think that this is a missing angle from the old statistical physics of the last millennium, that we did not at all address the question of data structure. And my conjecture is that really, to a large extent, the capacity of deep networks to perform well as they do in practice is due to the fact that they are seeing a world in the sense of the data that is presented to them in the input, the database, a world which is extremely structured. And that it is not structured randomly, it is structured with hidden manifolds, with a combinatorial structure, and that it turns out that this structure in layer that we have in the network is well adapted to handling the structure of the data. Let me show an example of that. If one looks at, for instance, the MNIST database of handwritten digits, so each digit is a vector in dimension 28 square, which is 784. And so this is the input space. Now, if I look at the handwritten digits, the ones which are here, and the tens of thousands of ones that are in the database, I could say, well, these digits, they are not arbitrary digits. You know, I could draw with 707 picture of 28 square pixels. I could draw whatever I want, even just keeping black and white. Only the first one on the left is a handwritten digit. So they are in the subspace of R to the 784. What is the subspace? It's not easy to define, but experimentally you can have some of its properties. For instance, you can estimate the dimension of this, what I call the manifold of the handwritten digits. And in order to estimate the dimension, there is a trick which has been developed, to the best of my knowledge, first in the theory of turbulence, to try to estimate the dimensions of strange attractors by Grasberger and Procaccia. And the trick is the following. Imagine that you have points which are in a space of dimension R, and you put P points in this space. Of course, in a circle of radius R, the number of points will grow like R to the D. It means that nearest neighbor distance will scale the total number of the points to the power -1 over D. So basically, by looking at the distance between nearest neighbors, or maybe second neighbors, or you can have more sophisticated tools, you can estimate the dimension of the manifold. And this works relatively well. And you find that typically for MNIST, the dimension is around 15. Might be 14, might be 16, but more or less it goes well. So it means that there are very large other space, complementary space to this manifold, in which the images do not belong to the world of handwritten digits for which your system has been trained. And actually, in such a case, the neuron should be trained to answer, oh, you have presented me this image here. It is not in my world. I don't want to answer you, if it is a 0, a 1, or a 2. It's foreign to my world. I have not been trained on that. If you look a bit more carefully, you can look at what are the 5. And the 5, they span a sub-manifold of the 15-dimensional manifold. It turns out to be a manifold of dimension around 12, etc. For each digit, you can see the dimension of the manifold. The 1 is easier. It's a manifold dimension 7 to 8. So geometrically, the MNIST problem is easy. You have a 15-dimensional manifold of unwritten digits. Within this, you want to identify the 10 perceptual submanifold associated with each digit, and they have dimensions between 7 and 13. All this from an input in 784 dimensions. Let me describe our attempt to generate a set of data, a generative model, an ensemble of a random database, which has some of these ingredients. And the idea will be that the input to my neural network, my image for a given pattern, for a given image, will be generated as follows. It is built from an internal representation, CR, and the CR basically gives me the weight of a superposition of basic features. So I have basic features. The features go from 1 to capital R. These features, they are vector in my n-dimensional input space, and each pattern will be will be built from a linear combination of the feature. So that would be easy. If you apply just a linear function like that, you will basically reduce your problem to the linear subspace. But the point is to apply a nonlinear function, a folding function. So I have here, I have this linear manifold of all the inputs that I can build from linear superposition of features. I fold it. And when I fold it, of course, I get a folded manifold, much more complicated, and this will be my input space. So it means that an input pattern, it has a latent representation, that is the representation in the latent space. And my hypothesis will be that, so the latent representation would be the one that you get in the 15-dimensional manifold of MNIST, for instance. And the assumption is that the desired output, the label, is a function of the latent representation. So, for instance, you could take a simple linear function, but it is in the latent representation. And your neural network does not know about this internal space. It does not know of the hidden manifold. It is hidden and it is folded, so it's not easy to detect. So you can look at relatively simple neural networks, and it will not be very deep because we have started with the elementary one. This is a network with 3 layers. It has n inputs, k units in the hidden layer, and then an output function. The output phi of x is a superposition with weight vk of what comes from the hidden layer here, and the hidden layer itself takes its input from here. You look at it from a set of data points which are built from which are chosen from a hidden manifold, and you can train it with a certain training error, a quadratic error here, or another loss function. And the target label is generated from latent representation. One point that I want to stress is that I favor this interpretation of the hidden manifold, but you can also have another representation of this same setup. And this other representation is the following. In my interpretation, I was looking at the input layer of the network is this one, and I am presenting these patterns here, which have some structure. They are living in a hidden manifold. An alternative of that would be to say, let me construct these inputs from a previous layer and put some auxiliary layer which contains the latent representation, and I project this latent representation to a larger dimensional space, and which will be my space of x mu, which will be the space of inputs. So if I do that, I have added one extra layer to my network with parameters Fri, which are the weights coming here, which are my basic feature vectors, which are quenched. They do not evolve. They are not learned. They are given once for all. So this has been studied a lot historically, because it is the first idea of random feature. That is, if you have a system, for instance, if a system which is not able to learn just a simple perceptron, and you have a non-separable task, one idea is to take your task and embed it into a larger dimension by using random feature, and then learn from the larger dimensional space. So what we do has the two interpretation of the hidden manifold and of the random feature. And in the case in which we are using not 3 layers of neuron here, but just 2, just a perceptron here, it makes connection with the recent work of Andrea Montanari and May. This problem is solvable in the thermodynamic limit. The thermodynamic limit is a limit where the size of the network goes to infinity, the size of the internal manifold goes to infinity, and the size of the database goes to infinity at fixed ratio. They all go to infinity simultaneously. It turns out that it can be analyzed. This is maybe the most important breakthrough that was done in recent months on all these problems, which is the fact that usually what we know how to analyze is a case in which the inputs, xi and xj here, are IID. In our case, the inputs are not IID, they have some correlations, and because they are coming from the same hidden manifold, but nevertheless, it turns out that if you go to the next layer, the local field, what we call the activation parameters of the neuron here, which is called lambda k. Lambda k is a weighted sum of the inputs. The lambda k here is just the sum of all the inputs weighted by the weight here. It turns out that in the thermodynamic limit, this becomes joint Gaussian. And because they become joint Gaussian, we can use all the tools from Gaussian random variables, and we can compute what is happening. I will skip the details on how it goes. This is called the Gaussian equivalence theorem that explains that. And we have applied it to 2 setups. One of them is what is called online learning. That is, you present at each time a new pattern, and you adapt the weights by just gradient learning. And it turns out that then you can solve the full problem in terms of the correlation matrices between the weights. And these are called order parameters in physics. And you can derive a set of ordinary differential equation that will solve completely for the dynamics of your problem. So for instance, the prediction here is a full line, and the small points that you can see are the result of the experiment to show that we have full control, full analytic control through this set of a few ordinary differential equations, analytic control of the generalization error. One thing which is interesting is that here you have these order parameters. Some of the order parameters is this one, which measures the correlation of the pre-activation of neuron K in the student and the weight in the latent task. They are in different space, so you have to project from one space to the other. But doing the proper projection, you can see the correlation between the student and the teacher. And you find that there are 2 phases in learning. In the first phase, basically, all these overlaps are the same, but then at some point the units of the students specialize, and you see that for instance the unit number 1 of the student aligns in the different space to the unit number 1 of the teacher, and the same for the 2 which align on the 2, and they decorrelate from each other, or the cross correlation go to 0. And this specialization is the moment when you really reach the perfect performance of the system. Another prediction that we have is that we can then study with this ordinary differential equation what happens if you increase the size of the student, and you find that there are these 2 plateaus. This is a transition where you have the specialization, and the specialization leads to a much better performance if you have a larger student network. And this is something that we have also observed experimentally, this time on experiments on databases, on learning in databases. This is with MNIST, this is with FashionNIST, this is with CIFAR, which is the same performance. I will skip the batch computation, just give you the result. You can compute in the case where your network is a simple 2-layer network, a perceptron. You can compute the generalization error in the case of square loss, and this takes this famous double descent curve. And in the case of logistic loss, you also see the double descent. One thing which is very interesting is that the peak of the double descent, it is exactly located at the moment where you have enough parameters that the size of the system is such that you can compute, that you can learn the database with 0 error, 0 training error. So you see this is a case in square loss. It has been observed quite a few times. But then if you do it with a logistic loss, then you see that it perfectly correlates with the peak of the double descent. So this was just the main part of the talk. Let me take 5 more minutes to add this appendix that I wanted to add, because I think that the times are such that one should really try to put some effort in all kind of aspects of trying to work on this virus. Maybe I had a special problem with this virus, and I wanted to try to contribute to something on that. The idea that we have been working on with this group of people here at Ecole and CEA in Saclay, and also with a lot of discussion with a group in Torino, and also a lot of discussion with a group in Mila, in Quebec, around Benjo. Our idea is the following. The idea is to try to see if one uses some application based on cell phones, an application that is able to detect possible contacts between people. Can we use such application in a slightly smarter way than what is usually referred to, which would be just, I have been in contact with an infected person and I am called by, I don't know who. So our program is to use information about individuals. Maybe information could be about age, symptoms or not symptoms, etc. This is known by each individual and can be stored on his own phone. And information about contacts, time, duration, which are known by 2 individuals in contact. And the question is, can you infer, can you get a good estimate of the probability that each individual is infected? It turns out that we had been working on similar problems years ago, and there are solutions based on message passing, the message passing that I was describing before in this talk, that can provide an efficient solution, which has a very big advantage. It is a solution that is based on elementary exchange of messages at the contacts. When you have a contact, you exchange basically 2 numbers between the 2 phones, and that's it. So you don't need any central system. You don't need any central computer that does the computation. You can just do it on a purely delocalized way, which helps a lot for privacy issues. I know that all this is There are a lot of issues about the possibility to do it in a and maintaining the right degree of privacy. I will not address this aspect. I just want to stress that if somewhere it can be used, then there are better use of it than just warning when you have been in contact with someone. The model that we have been using in order to develop the theory is a very standard model of susceptible, infected, recovered for epidemic spreading. Variants of this model are the ones that are used by epidemiologists. Generally, most studies, they do it in a kind of very rough way in which you have the number of susceptible persons, the number of infected, the number of recovered. Then you will have categories. You have susceptible of this and that age, infected of this and that age, maybe in the hospital or not, but they are global. Instead, what we have in mind is to describe it at the level of individual. That is, every individual can be susceptible, and if someone is susceptible, the evolution is that this person can become infected. Someone can be infected and then can infect someone other. And there are some removed individuals. Someone infected can be removed. It can be removed by several processes, hopefully by just being recovered. And the parameters are just the infection rate, what is the rate of infection from J to I at time t when there is a contact, and mu I, which is a recovery rate. Then the aim is to estimate the probabilities. Probabilities that each individual at each moment is infected, recovered, or susceptible. You can write very easily mean field equation for this problem. Let me explain you very briefly. Imagine that I know the probability that individual I is susceptible at time t. Well, the only way, and I want to estimate the probability that he be susceptible at time t plus 1. Well, the only way that he can, if he was susceptible at time t, he was not infected. And so the only thing that can happen is that maybe he will become infected. And he becomes infected. This depends on the contact, J, occurred at time t. The di of t are the set of contacts. And it depends on the contact and the probability of propagating the infection, lambda ij of t. And it depends on the probability that J, the neighbor, the contact that he has met, is himself infected. So this is the equation. And the other equations are just as elementary. You can use this mean field equation incorporating knowledge from contact infection, backtrack, in order to infer, to get some good prediction. There is a more elaborate version of that, which is dynamic message passing, which is what we had developed years ago. Just to give you an idea of the accuracy of these equations, they are not exact in general, but they are extremely accurate. This is what you get from prediction at time after 20 iteration of the process, 20 days later, starting from initial condition at time 0. 20 days later, this is a prediction for the probability that someone is infected. This is PI, estimated from mean field, and this is the one found experimentally by doing Monte Carlo experiments. So it's a rather precise framework. Using this framework, what you can do is basically identify, our aim is to try to see if we can help in identifying people who are not symptomatic, but who are already infected. Because these are the persons that should be identified, that should be tested, and that should be placed in quarantine if one wants to tame the development of the epidemic. So basically, in the protocol that we have here, we have a protocol in which we have identified the person who have symptoms and test them. And then for all these persons, we look at their contacts in the previous 5 days. And of course, if one could test all these contacts, it would be good. But typically, you will have factors of 100 or 200 people. I mean, for each person infected today, there have been 100 or 200 persons that he has met in the previous 5 days. And when the epidemic starts to develop, you cannot just test everybody there. And the idea is that among these 200 persons who have been the contacts, you want to identify who are the most probably who you estimate are the most probable to be infected, and you test them. And this is the result of what is happening. This is the development of an epidemic in a 10,000 population graph in a square. This is the standard epidemic without any quarantine. This is what you do if you just put in quarantine every day 7 persons detected with symptoms and 21 taken at random. This is what you do. The orange is the contact tracing. That is, you really take no longer at random, but among the contacts of the infected persons. And the green one is the mean field. That is, you estimate now using the inference from the mean field equation. And the dynamical message passing are even slightly better, but they are slower to run. This is another experiment obtained from a contact graph, which has been provided to us by Ferretti and Hinch in Oxford. We are interacting with them on their data. They have a very realistic model of SIR with various other compartments based on individuals. And so this is an extremely precious database. And again, you see that between the no quarantine, of course, is a disaster. The one with random testing is the blue, the one with contact tracing in the orange, and the mean field-based inference is there. So you see that you can decrease the peak of the epidemic quite a lot and delay the moment in which the situation you will lose control of the situation. So this is what we have in mind. Again, it can be done by just using these equations, these numbers, Pj infected, Pj susceptible, Pj recovered, can be stored on the phone or Mr. J, and you can exchange this information with the neighbors. So this is what I wanted to say. Sorry for having added this appendix, which was slightly aside from the main part of the talk, but not quite, because it is based on really the same set of ideas, which is using these mean field-based equation to do some sophisticated, complicated, large dimensional inference. So it is really in the same intellectual framework. And also to make this connection even a bit more precise. For instance, the group around Belgio in Quebec is working on developing a machine learning simulator that will simulate the epidemic and take the input from experimental data in order to be a simulator which is more and more sophisticated just by machine learning. So I think there are deep connections that are still to be explored for that. Sorry for being slightly too long, and I am ready to answer questions.
Thank you, Marc, for this great talk. So if there is question, you can probably first post them. So I think David can first open his mic and ask his question. David Ben-Simon.
Yes. Hello, Marc.
Hello,
Happy to
David.
see that you are fine again.
Fighting the virus.
Are you completely recovered, or are you still tired?
Yes, I am in the R phase, okay, completely.
Ah, okay. Good. So my question is regarding, you mentioned that there are many solutions that basically minimize the energy or even get it exactly equal to zero. What is known about the manifold of this solution? Is there some structure? Are they localized? Does it depend on the way you present the data? How many of them are they, etc., etc.?
Well, there are many people working on that. There are a few works on that, but at least for me, there is no clear picture at the moment. I mean, you have some people also at Ecole Normale, but in many other places who have been looking at that. There are some indications that that you have some kind of flat directions. That is, that you have reached a minimum and that you have some direction in which you can move and it will not change the performance. The problem, I think that one problem that we have, and it's my obsession these days, but one problem that we have is that typically we will have to, most of the work is very empirical. That is, it will take one architecture, one database, and one learning algorithm, let's say. And then you start to try to see, but it's hard to disentangle what is the property of the database, what is the property of the algorithm. The starting point of the algorithm is very important also. It turns out that in most cases, the stochastic gradient descent, they don't go very far from the initial starting point. So I don't have, at least for me, there is no clear vision on this question at the moment. It's one of the main problems that is around.
Okay, thank you, Marc, for this answer. Any other question? I guess everybody is a bit shy to ask question in front of such a large audience. Okay, maybe I can at least ask. I have several questions, but I will just ask one. So you mentioned results regarding 2 layers. Are there results with more layer, or even maybe like on recurrent networks where statistical physics can be useful, like residual networks or this kind of things?
Yes. So we have results on these networks here, which have at least, okay, they have an input layer, an output layer, and a layer of hidden units. So this is already non-trivial, let's say. We have a result for this. Both the main result that we have is with online learning, but the method that we use for batch learning can be applied to these. We don't have the result yet. I think that extending these results to multi-layer case is still a main challenge. We are thinking of this and working on doing that. It's not yet quite clear to me how it can be done. But one thing which is important is that this Gaussian equivalence theorem is a very powerful tool, actually. And we have not yet found how to use it iteratively when you have several layers. But there might be a way to do it. It's not yet found.
Okay, so I guess we'll stay tuned for more results in this direction in the future. So Olivier Peltre has a question, so maybe he can open his mic.
Yes, hello.
Hello?
Yes, hi, can you, okay. Thank you, it was very interesting. I was wondering if you could elaborate a bit on the relationship between the spin classes, which you talked a lot, and the deep neural networks. Because one main difference between the two seems that you have this input-output structure, this feed-forward direction in the deep neural networks, whereas these spin classes are completely symmetric and energy flows in every direction. And so when you have these energy terms going from the error and the input-output of your neural network, how can you make this fit with this spin class model?
Yes, so you are right. I was, of course, I was forced to take a very big shortcut. That is, I went directly from the spin glass case to something to what I have put now on the screen. It turns out that starting from the initial studies on spin glasses, which of course for us it has been the kind of basic moment. It is the moment in which we physicists have started to understand the behavior of large dimensional spin systems with random interactions, with a strong disorder and interacting systems. So for us, it was a kind of a strong building block. It turned out that you can use the same tools, the same ideas, and a lot of the methods developed for spin glasses. You can use them in a more general context. Most of what I've been saying is a context in which you have an equilibrium, you have a probability distribution. So for instance, this is the problem of learning shown in an abstract way, but it is exactly the problem of learning in a feed-forward neural network, or in general in machine learning. You have, given the database, you have a probability distribution in the space of W. It means that you have an energy, and you see this energy, of course, it does not at all have the form of the spin glass. It's not of the type Wi, Wj, it's not a binary energy. But there had been a lot of development starting from the initial program of spin glasses in order to look at spin glasses with multi-spin interaction, which finally with arbitrary function of the spins as energy. And this is what we have here. We have exactly that. We have an arbitrary function of the W. It's not completely arbitrary, but it's a well-known function, well described. And for this, we can use the tools of spin glasses. So it does not, I mean, there is a whole long chapter of a couple of decades of development of spin glass theory, which went from the simple spin glass Hamiltonian, where you have binary spin interaction and the symmetric interaction, and you go to something which is more sophisticated and much more general, which is what I am writing here, which is a general function of the W.
Okay. So if there's no more question, I think we can all thank Marc for his great talk. So before concluding this session, let me just say that the next event will most likely be on June 9th, although it's not yet confirmed. It will be posted on the website of PRAIRIE, so please have a look if you want to follow the next event. And it should be Alex Christia, who will speak about speech learning and supervised learning during children development. So I think it would be also very exciting. And also, before concluding, I would like to thank a lot Catherine Grangette from Ecole Normale, who helped a lot with setting up this talk. So stay tuned, everybody, and stay safe. And once again, thanks a lot, Marc, for this nice talk and for doing it for the first time. It was really amazing. Thanks, everyone. Bye.
Bye-bye.
Merci beaucoup, Marc.
Thanks.
Avec plaisir.
Au revoir à tous, merci.
Merci Marc, merci Gabriel, je ne sais pas si vous êtes encore là.
C'est Jamal?
Oui, merci beaucoup.
Salut, à bientôt.
Salut.
Ouais, salut à tous,
tu es encore là? Bon, bah, je te contacterai sur un autre sujet, Marc, du coup.
Ok, quand tu veux, on s'appelle.
Ok, ça marche. À plus tard.
Merci à tous. Merci beaucoup, Marc.
À bientôt.
Au revoir.